I'm LuAnne Thompson from the School of Oceanography here, and I'm what they call a physical oceanographer, so I know about the physics of the ocean. In terms of the salinity, there's the impact sort of just having the salinity change on organisms. The salinity change they're talking about is pretty small. There is a potential impact on changing the vertical structure of the ocean, so it's harder to get exchange from the upper ocean to the deep ocean. And that happens both because of warming, and if you make something saltier or fresher, you can change that sort of difference, if you will, between the density at the upper and the ocean and the lower ocean. So both of those things can have impact. It's more subtle, though, I think, than just changing the salinity and affecting an organism, like would happen if you change the pH of the water, which is a more profound impact. So as Dennis said, I'm going to talk about models and projections. So first of all, I want to talk about why we use climate models, because often you hear about questioning about global warming and projections because it's just models. The reason we use climate models is to understand what controls climate on these long timescales, to explain natural variability, like El Nino is one that most of us in the Pacific Northwest are familiar with, and then to make, not projections about what might happen to the Earth's climate in the future. I need an editor for my stuff. So this projection part is what I'm going to be talking about. And notice I'm not saying predictions, because we don't really know what's going to happen, because we don't know how much more carbon dioxide we're going to put into the atmosphere in the future. Projections are controlled by a couple of things. As I said, they're controlled by how much humans will influence the composition of the atmosphere, land use, etc. So to project that, we use, by we, I mean groups use demographic economic models to develop scenarios of how we think the world might develop in the future. And that tells us something about how human activity can influence climate, because we know energy and carbon dioxide are closely linked to each other. So in general, if you have more economic growth, you're going to burn more carbon unless you introduce new technologies like we see in this building here. The projections are also controlled by the physics of the climate system. The atmosphere, the ocean, the snow and sea ice cover, the biosphere, both in the ocean and on land. So you have all these components of the climate system that you want to hook together and then project out in the future. But basically, I mean, it's actually pretty simple, and as Dennis said, the radiative properties of the atmosphere are very well known. But basically, we use the climate models to solve F equals ma. You remember that from high school physics. How those currents and winds move things around, the radiation properties of the atmosphere, phase changes of water, whether things are evaporating or freezing, chemical and biological interactions, and then we project the winds, the currents, the temperature, the rainfall, the pH, the ice and snow cover using the models.
Yeah, sorry.
Yeah.
I never took high school physics, so what is F equals?
Force equals mass times acceleration. Okay, so that's sort of the basic law of physics that most people see in high school. So how much carbon dioxide will be released in the atmosphere? So this is the first step, developing these demographic, economic scenarios, if you will, of what's going to happen in the future. These scenarios have been used for the last 15 years, something like that, Dennis? And we have a whole new set of scenarios that have been used over the last couple of years for climate models and will be in the next IPCC report. We have different scenarios. We have B1, so this is carbon dioxide emissions. So this is how much we're emitting per year, and once again can be tied to energy usage and sort of on a basic level. So here's B1, basically utopia, where it goes up a little bit more and then comes down again. This is A1B, where most of the projections use this sort of middling scenario where it goes up and then comes down towards the end of the century. And A2, which is often called business as usual, which is sort of the more catastrophic scenario. And then over here is the concentration of carbon dioxide given by these emissions. Okay, so it's a cumulative thing. It doesn't go down immediately, the concentration, but accumulates in the atmosphere over time. Okay? So right now, for instance, we're putting in 9 gigatons of carbon a year, something like that. and about half of it stays in the atmosphere, a quarter goes into land biosphere, and a quarter goes into the ocean, okay? So here are our scenarios, and remember we said, okay, today, I looked yesterday on a website, it's almost 400 parts per million. There's a seasonal cycle, you saw that thing going up and down. Pre-industrial is about 280. Here's 280, and here's where we're going into the future. So end of the century, A2 is like 800 parts per million. Okay, so now we have to start thinking about climate versus weather. So we take these models and we integrate them on very big computers over time. And by integrate, I mean step forward in time. We start at day 1, then we go to day 2, then we go to day 3, and so on. So we know that weather forecasts are reliable for more than a few days or a week or so. So how can we hope to predict climate hundreds of years in the future, or project? So the answer is that the climate is the average of weather. We're not trying to predict a storm that will occur in 2015 on September 5th. What we're trying to do is talk about the average of the weather, or average system. The climate models do include weather. So there is weather in climate models, but we do not expect them to predict the exact progression of weather from day to day, okay? Instead, they predict the average evolution of temperature, rainfall, et cetera, over decades. Okay, so there's a difference there. And fundamentally, these climate models are pretty similar to forecast models that we use to forecast the weather. So once again, what's contained in the climate models? There's pieces. One is the atmosphere, the ocean, the biosphere, and what we call the cryosphere, which is all the snow and ice, sea ice, land ice, et cetera. So the other thing that I think is important to know, and hopefully this will not be too confusing, is to do this, we break up the globe into grid boxes. So we make a grid box that each is 100 kilometers by 100 kilometers, say. So think about how big the Puget Sound region is. I don't know, how far is it from here to Olympia? It's like 60 miles, something like that. So that's about how big. We have one representation of winds, current, temperature, humidity over that sort of whole region. So it's a very coarse picture. And then we break it up in the vertical too, in different layers, both in the ocean and the atmosphere. And then we step forward each of those grid boxes day by day. And then it also includes parameterization of things that we don't directly model. So like if you look up in the air and you see clouds and you say, well, wait a second, you only have one point to represent clouds in this 60 mile by 60 mile box. So what we do is we develop physical models, representations of the cumulative impact of things like clouds. Okay, so now I keep on using predictions. Change that to projection for this century. So if we look forward to the rest of the century, for some of these scenarios, this is what we see. Okay, so this is global surface temperature warming, and it's tied to this year 2000 value. I think the zero, I don't remember when the zero is, maybe 1980 or something like that. And then we look forward in a century. Now, the pictures I'm using here are from the 2007 report, which is why it starts in 2000. And I'll talk about the next report briefly in a few minutes. So here's my utopia projection. Okay, here's, let's see, the A2 is sort of the disastrous, 4 degrees C. Here's my translation in terms of Fahrenheit over here. And then here's let's see, where is A1B? A1B is the green, and I'll show you some projections from that. Right now, we're on this trajectory, or even a little bit above it. So the temperature, on average, will rise by somewhere between, well, it's not going to be 1 degree Fahrenheit, but up to 6 degree Fahrenheit or more by the end of the century. Okay, so if we go back to here, we ask, well, where does this spread come from? These lines here represent the spread of what the projections are. And it's important to understand where those spreads come from. The spread here is from this demographic, economic uncertainty about what people will do. Those are basically our choices. And then there's a spread between different modeling groups here. And then there's also natural variability. Okay, so there's natural variability, the choices we make, and then the spread between different modeling groups. So I should have looked up how many different modeling groups. Do you know, Dennis? Like 20 or something around the world? Yeah.
There's actually multiple models at each institution,
Yeah.
so the number of models is pretty large.
Yeah, and all of the data from these models is at an archive that anyone could download and look at. Okay, so the differences between the climate models, there's three big US modeling groups. NASA GISS, which Dennis talked about, a NOAA model at the Geophysical Research Lab in Princeton, New Jersey, and an NSF model at the National Center for Atmospheric Research. In how much climate warms for a given increase in heat trapping gases, mostly attributable to clouds. And then there's natural climate variability like El Nino. Okay, so what else do we know and what else do we predict for the future? The ocean acts to dampen warming by absorbing heat, and because I'm an oceanographer, I pay attention to this number right here, and this is the rate at which the ocean is absorbing the heat. Okay, so it's constantly absorbing the heat that is the warming atmosphere gives it, basically. Remember that the heat capacity of water is much, much bigger than that of air. I always say that I'd rather have a hot water bottle in my bed than a hot air bottle because it'll keep me warmer for longer. This 0.6 watts per meter squared is the excess heat that's going into the ocean. And basically what this means is the climate system is out of equilibrium. There's not a perfect balance between incoming and outgoing radiation, right? Incoming or outgoing heat. So this amount of heat, my husband just actually came up with an analogy, is about like every person on the planet holding about 24 hair dryers and running them at full blast all the time, okay? So that's the amount of heat, excess heat that's going into the ocean. Half of the current sea level rise from warming is the current sea level rise is coming from the expanding ocean. So when you warm water, it expands. So that's an important piece. And the other thing is that we're out of equilibrium. So because we're out of equilibrium, even if the concentration of all greenhouse gases is kept constant, a further warming of about 0.6 degrees C is likely to occur by 2100. So the ocean warms up enough that the whole climate system can radiate the same amount of energy to space as it's taking in, okay? And the other thing is that sea level will continue to rise for centuries with constant greenhouse gases because the entire ocean needs to warm up for the energy budget to be in balance. So you have to basically warm up this entire 4 kilometer column of water in order for the climate system to come into true equilibrium. And if you're warming up the deep waters of the ocean, you're expanding them and sea level will continue to rise. This is not because of ice sheets and things like that. The other thing that the models tell us is that warming is not uniform. So this is my A1B, the middle scenario there. This is a spatial map of the warming over the globe. You can see that it's warming everywhere by the end of the century, and that you can't see on this plot, but all the models agree that it's warming everywhere, okay? Because everything is yellow to red. And it's warming more, I keep doing that. It's warming more in the northern hemisphere over land, and warming a lot over the Arctic, a little bit less down here. We could talk more at break why that might be. And basically warming everywhere by 3, 4, 5 degrees C. But there is a spatial difference in terms of how much it's warming. The next thing to talk about is the predictions for rainfall. And Dennis is more of an expert on this, but what I did is I took the forecast from yesterday through out to 2 weeks. And what's interesting about the forecast here is that when you look, you get a high and a low temperature out 10 days, right? And we know that's not really accurate, but what they give you in terms of rainfall is a percentage of a chance of rain, right? They don't tell you how much it's gonna rain or when it's gonna rain. They tell you the percentage. So it's sort of inherently less certain. And they said that it was gonna rain a lot yesterday during the day, but it didn't rain a lot till last night. This blue is where there's negative precipitation minus evaporation. Look at South Africa, West Australia, and then over in Brazil. And then I'm going to show you projections of how much this will change in the future. And you can see why I picked out these spots. I circled them because the globe is rotated in this picture. So this is changes in summertime rainfall at the end of the century. The wet is going to get wetter, so the blue is where it's getting redder, and the yellow-orange is where it's getting drier. And as Dennis said, the wet gets wetter, the dry gets drier. And in particular, if you look in Brazil, South Africa, West Australia, you see this drying. Now these little stars here are where the models agree with each other about what rainfall will do. And you notice that there's many places on the globe where there's not agreement, right? Unlike for the temperature projection where all the models agree, pretty much. Okay, so you get this much less agreement in rainfall, but you do get this general pattern of wet get wetter and dry get drier. So I did, I should have projected it, but I did blow it up earlier. And we're actually in kind of a 0 point. Nick will probably talk more about that, but it's not a very interesting place in terms of the globe.
Oh, I don't know about that.
But it's not like we're going to have this kind of drying that you might project.
For the year as a whole.
This is summertime, but yeah. And there's very important seasonal differences between summer and winter. And so if you look at overall year as a whole, it's not a very interesting place, but I'll leave that to Nick. He will tell you the subtlety of what it's going to rain more in the summer and less in the winter. Is that right?
Less in the summer.
Less in the summer. Oh yeah. See, this is why I'm not talking about that. Okay. So, but I think I got my point across. We know rainfall less than we do temperature. And that the reason why I highlighted these places, in particular sub-Saharan Africa, that's problematic from a global perspective. So now I wanted to just talk a little bit about why extreme events may be more likely. So it was kind of nice that there was a rainfall record here yesterday. We had a little over an inch of rain, and it was a record for September 5th rainfall. So when we think about extreme events, we think about sort of a distribution, a probability distribution. And the way you read this is you say, okay, I also put the average temperature here for September 5th, the high temperature that you might get, and the low temperature that you might get. And you can see that this kind of goes from the high to the low with the average in between. So what this says, if say you have 100 years of September 5th temperature. The average of all those 100 years is going to be right here, and maybe 20 of those years will be right in this area, and there might be a few years down here that are in this sort of 39 degrees to 43 degrees, and a few that are in this high range. Now, if you imagine changing the average temperature and moving this distribution to warmer temperature, you would expect to get more record hot weather, or a nice little outlier in rainfall, and fewer cold events. So you're going to experience some heat waves that you maybe not ever experienced before. Or you can think of it as a return period with, like, say with floods, they say it's a 100-year flood. A 100-year flood may turn into a 10-year flood. So that's another probabilistic way of talking about it. So the return period of extreme events becomes shorter. Okay, so what about extremes? Dennis talked about this earlier. By the end of the 21st century, warmer and fewer cold days and nights, more frequent hot days and nights, more warm spells, heat waves, and heavy precipitation events. By that we mean the proportion of total rainfall from heavy rains. And once again, I'm going to use yesterday's example. The average rainfall for September is about 1.5 inches in Seattle. We got 1.1 inches yesterday. Okay, so you can imagine concentrating that rainfall in fewer events, and that's what that means. More increased incidence of extreme high sea level or storm surge, and that can also be thought of as this distribution thing. Think about Sandy. Nick can talk more about Sandy later, right? I wanted to talk about the next IPCC report. It's coming out September 27th. You can download it from the website, and I will give you the website. Things to look for in the report. You can't ask Dennis about it because he's one of the authors, but this is what I've gleaned. New emission concentration scenarios, so you'll see RCPs instead of these SRES scenarios, so that'll be a little bit different, but there's kind of similar, there's things that are similar to each other. Discussion of ice sheet contribution to sea level rise will be more complete. Evidence for deep ocean warming and these sort of warming not just at the surface, but at depth and all the way down to 4 kilometers. More discussion of ocean acidification and the biogeochemical changes you might see on land and in the ocean. More information about clouds and aerosol interactions. And then there's this recent hiatus, there'll be some discussion of that, although the literature is changing. There was an important paper that came out a couple of weeks ago about how the tropical Pacific is the answer to why this hiatus has happened. Okay, so it's released September 27th, www.climatechange2013.org. You can download it. It'll be like a 30-page document that should be fairly readable. Seattle lead authors, I thought this would be useful for you guys. Dennis Hartman, who you now know. These are the names of the chapters they're on. Greg Johnson's my husband, that's why I know some of this stuff. Greg Johnson and Dick Feely from NOAA PMEL, Observations of the Ocean. Chris Savine, Carbon and Other Biogeochemical Cycles. He's an expert in marine carbon cycle. Chris Bratherton, Clouds and Aerosols, who's in the same department as Dennis. James Overland, NOAA PMEL, Detection and Attribution of Climate Change from Global to Regional. He's an expert on Arctic. So there's local resources for you guys after September 27th, which they really can't talk before then, but the official release will be then. So, okay, I think I'm done.